Welcome everyone. I am Ken Clairbout, K4ZW. Glad you could join us this evening or morning, wherever you are. As most of you know, we do have a Q&A session at the end of the presentation. You're welcome to submit your questions at any time, but we'll hold them here until the end of the presentation, and Carl can go ahead and answer them then. So, most of you who have attended webinars before or been to Visalia, Dayton, or other conventions know our presenter this evening quite well. Noted propagation guy, contester, DXer, all-around good guy, Carl Lutzel Schwab, K9LA, is with us this evening to take a look at whether we're heading into another Maunder minimum and what it means for propagation. So, Carl, we are very happy to have you with us this evening, and looking forward to lots of good data and presentations. So go ahead and take it. The floor is yours.
Okay, thank you, Ken. Hello to everyone, wherever you are. And my name's Carl, K9LA, up in Fort Wayne, Indiana. And tonight we're going to talk about are we headed into another Maunder minimum, and talk about if that happens, what does that mean for propagation. Let's see if this thing advances. Yes, it does. Well, first of all, thanks to the Worldwide Radio Operators Foundations for sponsoring these webinars. I think they're great, and it's a great way to learn about everything. If you can, please support them. Their websites, they're at the top of the page. Okay, what we'll talk about is, first we'll just give a very quick update on cycle 24. Then we'll get into the meat of the topic tonight. What is a grand solar minimum? A quick review of the Maunder minimum. Review of many solar parameters pertaining to grand solar minimums and Maunder minimums. And then we'll kind of take a look at what might propagation look like if we do enter a Maunder type minimum. Then we'll do a summary, and that'll be it. First, we got a little pop quiz, and what I'll do is answer this at the end of the presentation. What do the call signs W2XBS and W3XE have in common? Now, these aren't I don't think they're recent call signs, but they're kind of old, and the X at the beginning is probably the big clue. And if you've been licensed for a long time, you might know what that clue is. Okay, quick update on cycle 24. What we're looking at is a plot of the monthly mean solar flux. That's the vertical orange bars, and also the smooth 10.7 centimeter solar flux. That's the blue line. This data is up to date and includes the March monthly mean, which then translates into the September 2013 smooth value. And as you can see, and probably I hope you've experienced, that we've had some pretty good propagation on the higher bands in late 2011 and late 2013. And there's two reasons for that. Is the monthly means were very high in those fall-winter months of 2011 and also 2013. And also the atmosphere changes composition throughout the year, and it's pretty much best for ion production in the fall, winter, and spring months. So if you're going to have lots of solar activity, the months to have it are in the fall, winter, and spring months, because that ties into the atmosphere too. And that happened, and we've sure had some good 10-meter openings, at least up here in Fort Wayne, long path into Southeast Asia, not just JAs, but a lot of others. As you can see in the smooth blue line, the first peak of cycle 24 will likely be pegged at early 2012. Then we kind of decreased a little bit and stayed down there, but now we're in the process of a second peak, and it's even higher than the first, as you can see. And this likely will extend good propagation until the end of 2014 at least. We'll just have to wait and see what happens, but I think the contests this coming fall are going to be still pretty good on the high bands. after that, we'll have to wait and see. This is the same picture, but in terms of sunspots. And you can see there are the same trends as the 10.7 centimeter solar flux. Very high monthly means in the fall of 2011 and also in the fall of 2013 and extending into the early 2014. So everything says, get on the higher bands right now because who knows what's going to happen later. Here's a look at all 24 solar cycles in recorded history. The average solar cycle magnitude is about 112 of all those 24 cycles that we've said are the official records. Now that's not a lot of data points, but the cyclic trend in that data suggests we are entering a third period of small solar cycles. You can see the first period of small solar cycles, cycles 5, 6, and 7. They began 12 through 16 or so. And just for the record, the longer, we're all aware of the solar cycle 11-year, and of course there are other cycles. If you look at older solar activity, the Gleissberg cycle is around 8 solar cycles, so that puts it around 90 years. So that's from that first minimum period to the second minimum period. It can also apply to the 3 maximums that we see also. So what is a grand solar minimum? Let me get rid of my little, whoop, that didn't work. There it went. So what is a grand solar minimum? And it's a period of at least several solar cycles that are of less than average magnitude. And I believe that's a pretty accurate description or definition of it. This is the same plot, but just added some more annotations to it. The red line is the average of 112, and you can see 5, 6, and 7 were certainly quite below average. Cycles 12 through 16 were also below average. Now that first minimum is called the Dalton minimum. The second minimum, I don't know if there's a name for it. I seem to remember seeing a name once, but it didn't stick in my memory, so I'm not sure if it's been named or whatever. But usually the grand solar minimums are named after the person that kind of discovered them. Now that's a pretty loose term, but that's how they're named. So there's recent grand solar minimums. In our official records, we've seen 2. Oops. Okay, I got to hit the thing again because, there we go. Now here's some earlier grand solar minimums. If you've seen some of my other presentations here, you've probably seen this one before. What it is a plot of solar activity from about 800 AD to 2000 AD, or a little bit before that. The vertical axis is the change in carbon-14 in tree rings. And on the right there's a little explanation. When we enter a solar min period, the sun's magnetic field is weakest. What that allows is more cosmic rays into the Earth's atmosphere. Now these cosmic rays are very energetic, which means they're going very fast. And they create secondary particles by collisions with the constituents in the atmosphere. And what happens is beryllium-10 is deposited into ice cores and carbon-14 is in tree rings. And that's how we can kind of tell what the sun has been doing way back when we obviously didn't have any sunspots or any other measurements. Now, note that these 2 proxies are out of phase with the solar cycle, which means if there's a positive concentration of beryllium-10 and carbon-14, that indicates a low solar activity. And you can see those high carbon-14 concentrations corresponding to minimums. There's the Dalton minimum that was in the previous slide. There's that second minimum after that, again, I'm not sure it has a name, but the one we're probably most familiar with is the Maunder minimum from about 1645 to 1715 or so. And there were ones even before that. And again, the names are after the people who kind of discovered them. Sporer minimum, Wolf, Oort. Now, according to this, the Maunder minimum has been the biggest one that we're aware of. The Dalton minimum looks like it's kind of somewhat equivalent to the Wolf, not as low a minimum as the Oort minimum, and the Sporer minimum looks like it's about the second biggest minimum that we think we're aware of. Again, I got to stress that these are just the beryllium-10 and carbon-14 are proxies for true solar activity, but they appear to be very good. They're a coarse measurement. They don't allow us to determine what a single solar cycle looked like, but they can tell when there's been a period of low solar cycles or high solar cycles. Note that the data only goes to about 1950, and we'll talk about that a little bit later. And here's the lowdown on the Maunder minimum. That's the one on the left there that's annotated. The Maunder minimum had very few sunspots, and we'll talk about that a little bit later too. The recent grand solar minimums, there's the Dalton and, with the 3 low cycles, and then there's the other one with some low cycles. They had a fair amount of sunspots, but they're all classified as a grand solar minimum because their magnitude is below the average. Now, we've kind of assumed that the Maunder min is just an extreme form of a grand solar minimum, but I'm not sure that's true. It's kind of like solar flares and coronal mass ejections. Before the space age arrived, where we got satellites up there to better monitor the sun, I think everyone believed that solar flares and coronal mass ejections occurred concurrently. But since then, we've, thanks to a gentleman named Gosling, he showed that really solar flares and coronal mass ejections don't necessarily occur together. You can have solar flares and no CMEs. You can have CMEs and no solar flares. Now, they may be rooted, their cause may be rooted in the magnetic field on the sun, but still they appear to be two different things. So it very well could be a Maunder min is not a grand solar minimum, or at least not the same process. It would be nice to go through one to maybe get some measurements and kind of decide on that. Okay, now there have been many articles on the Maunder min in the technical, the scientific literature, and also in public. And what I've done is the next 2 slides kind of list some of the big ones. And these are the articles we're going to talk about in relation to why the authors believe that maybe there's a Maunder min coming for us. Feynman and Rusmakin in 2011. They created criteria for Maunder-type minimums versus just a normal Gleissberg cycle. So remember that earlier plot. The Gleissberg cycle says we're probably in for some low solar cycles, but are they different than the Maunder-type minimum? And that gets back to the question: is a Maunder min just an extreme form of a grand solar min, or are they something different? And what they concluded is we're not really seeing a Maunder-type minimum coming. Svalgaard in 2012 looked at Nobayama data. One of the key things he pointed out was that the Maunder min was not due to a lack of observations. You always got to bring up those questions for data that's centuries old. How good is the data? But using auroral activity, etc., it's very obvious now that the Maunder min did not have sunspots, and it wasn't because nobody was looking or we had cloud cover a lot and we couldn't see them or whatever. And Svalgaard also pointed out that the Maunder min is really not a deficit of magnetic flux, but it's just a lessening of the efficiency of the process that compacts magnetic fields into visible spots. Now that may be happening again, and we're going to get into that a little deeper in a subtitle called Disappearing Sunspots. Steinhilber and Beer in 2013 predict a period of low activity until about 2100. Not time, but the year 2100 AD. Dr. Hathaway at the Huntsville Hamfest last year said cycle 24 is probably going to be the smallest in 100 years, and cycle 25 is going to be even smaller. Again, we're going to get into this stuff in a little bit here. The second slide with more articles, McCracken and Beer noted that the 2006 through 2009 cosmic ray intensities were not as great as prior grand solar minimums. In other words, the sun's magnetic field was not as low and thus didn't let in as many cosmic rays. Vaquero noted that prior to the Maunder min there were 3 descending cycles, subsequently descending cycles that led into the Maunder min. One that you might have seen because of its publicity recently was by Jim Papa in 2014 on the Forbes Online website. And he cited 3 issues that could say we're getting into a Maunder min: hemispheric asymmetry and sunspots, weakening of the polar magnetic fields, and a decline in the sunspot's magnetic field strength. So those we'll talk about 2 here. And then Livingston and Penn in 2009 made a really interesting case that sunspots are disappearing, and we'll get to that. And then Altrock in an Air Force Research Lab paper in 2012 noted that the rush to the poles, which comes from iron 14 emission data, was very slow and intermittent for cycle 24, very abnormal compared to previous cycles. So with those brief explanations of the articles, let's get into some details of each of the articles. The first one is a Maunder type minimum. This comes from the first paper, trying to define criteria between a Maunder type minimum and a Gleissberg cycle, or just a low solar cycles per the Gleissberg cycle. The Maunder type minimum, its duration is quite intermittent, 90 to 100 years. Its duration is varies wildly from 20 to 190 years. It's distributed randomly in time, so it may not be when you'd think the Gleissberg cycle says there's supposed to be low solar activity. The onset of a Maunder minimum can be abrupt or follow a few decreasing solar cycles. Sunspot numbers are extremely low. As we saw, the Maunder minimum had few sunspots as compared to the Dalton minimum, where we saw numbers 50 to 75, kind of like what we're experiencing now. The galactic cosmic rays that get into our atmosphere are very high, and mid-latitude aurora is extremely rare. Now compare that to some characteristics of the Gleissberg cycle. Period's about 90 to 100 years, and we saw that in that earlier data. And that translates to about 8 11-year solar cycles. And we're due for an extended period of low solar cycles. The maximum sunspot numbers are below average, but not 0. And the sunspot number returns to nearly the same low value at 11-year minimums. So we can see that we're certainly headed for a period of low solar cycles. Still nothing definite about a Maunder type minimum, though. Okay, the next paper was about low activity until 2100 AD, and the authors based their conclusions on 9,400 years of spectral analysis of carbon-10, beryllium-10 in ice core samples, and carbon-14 in tree rings. And of course, it assumes the sun will continue to vary with the same periodicities for the next centuries, which, you know, that could get you into trouble, I bet. We'll just have to wait and see what happens with them. One paper talked about the 2006 to 2009 cosmic ray intensities were not as high as previous minimums. Unfortunately, I have never found updated data on that plot showing what the carbon-14 looks like out to 2014. I'm still looking for it. There's my extrapolation of probably what it's going to be. Suggests that the minimum will be worse than the Dalton, but maybe not as bad as the Maunder minimum. Okay, Dr. Hathaway's prediction at the Huntsville Hamfest. He didn't have very good news for high-band aficionados, and most of his work is based on decreasing polar fields, and we'll see that in a couple slides down the road. He also prefaced his presentation with the following on the second slide. It said, "Don't shoot the messenger." Everybody has to remember he's just reporting, and of course the sun is the root cause of everything here. One of the papers also described the Maunder minimum was preceded by 3 descending cycles. And what they had to do was review old data and use some newly found data prior to the Maunder min. Now remember, that's, you know, these sunspot cycles are before our official cycle 1 started. So you got to question how good the data is. What they concluded was cycle -9 was not as high as earlier thought due to a sparse amount of data. In other words, somebody probably just extrapolated, saying, well, maybe it was about this high or something like that. And they believe it wasn't. Now, the negative sign in front of the cycle, like cycle -11, just signifies that it's the 11th cycle prior to cycle 1. Maybe 12, I'm not sure, but whatever. So cycle -11 had a group sunspot number about 120 at maximum. Cycle -10, in other words, we're getting closer to the Maunder min, had an R sub G of about 35. And then cycle -9, the one that they had a contention with, had an RG of about 20, which was originally thought to be about 80. So these 3 descending cycles appear to have preceded the Maunder min. So let's take a look at our recent data, and what we're seeing is 3 descending cycles now. If you want, you can count. We've even seen 4. What I've done is added in cycle 24. It's probably going to be around 75 for a smooth sunspot number, the max of the second peak. So perhaps this suggests that we are headed into a Maunder minimum. Note that the Dalton minimum did not have 3 descending cycles. It had 2 and then went very low. You know, do you count cycle 5 as the third one? I don't know, but just looks more like our descending solar cycles nowadays. Maybe a better indication that we are approaching a Maunder type minimum. Hemispheric asymmetry. This was expressed in another paper, and when the sun's magnetic field is about to enter a grand minimum, or is leaving a grand minimum, we see more sunspots in one solar hemisphere than the other. This comes from an applied mathematician over in England. This one I had a little trouble with. I'm not, maybe I just don't understand what he's saying. Just because if you look at past hemispheric asymmetry, in other words, how many sunspots were in the southern solar hemisphere, how many were in the northern solar hemisphere. And as you can see, it's prior to solar minimums, there seems to be a lot of asymmetry. But during that period, there really wasn't a Maunder minimum or even a grand solar minimum. So I'm not sure I understand what his point was in that paper. Notice that on this plot, the cycle 24, way on the right, was only had data up to the kind of the ascending phase of cycle 24. Here's a little bit more data. Whoops. Okay, on cycle 24, and what it is solar sunspots by hemisphere. The northern sunspots are blue, the southern sunspots are red, and you add them together, you get a full solar cycle in green. You can see why cycle 23 had a second peak. It was because the sunspots in the southern hemisphere of the sun had a peak, and that gave us the second peak for cycle 23. Now, cycle 24, the northern hemisphere dominated early on, and since it peaked in about, well, this is the horizontal axis is months past the left axis there, left y-axis. But you can see the blue, the northern sunspots have kind of been decreasing ever since. And why we're seeing a second peak is because the southern solar hemisphere has been very active. So, well, there's a lot of asymmetry, and I'm not sure what to say here, if that says we're entering a Maunder min or just a grand solar min or whatever. It's happening, and hopefully when we get some more data, we'll be able to maybe figure it out. Okay, I talked about polar magnetic fields. That's one of the big ones by many of the authors. What it is just horizontal axis is time starting January 1976 up to the end of December 2014. Of course, we're not there yet. But note that the magnetic field of the sun reverses at solar max. That's what the red arrows pointing to when the polar field goes from plus to minus or minus to plus. And of course, it's very obvious that the solar polar fields are decreasing. They were quite strong for cycle 21 and 22, but after cycle 23 max, things just didn't pick up, and they're pretty low. This also shows that the sun really has a true 22-year cycle when the field on the sun is again aligned as it was before. It takes really 22 years for that to happen. Disappearing sunspots. This is a really interesting paper, and it may have a good deal amount to do with what's going to happen here if we are going to enter a Maunder minimum. Livingston and Penn, what they did is they measured the magnetic field strength of the fields around sunspots. Okay, so a good question is, how the heck do you do that? Well, there's a gentleman named Zeeman who came up with a way to do that. He noted that one of the spectral lines of iron splits under the influence of the sun's magnetic field, and how far the spectral line splits apart is correlated to how strong the magnetic field is. If you want to look at that, just Google Zeeman, Z-E-E-M-A-N, splitting, and you'll see a lot of interesting information about that. So what Livingston and Penn have been doing is measuring the magnetic fields of the sunspots since about 1990, 91, 92, and in their paper in 2009 they presented data up to 2009. And as you can see, when you add a trend line, the magnetic fields of the sunspots are decreasing. What they also pointed out is when the strength is less than about 1500 Gauss, we're not going to be seeing sunspots. They're not going to be dark to contrast with the rest of the sun. Now, Svalgaard, who I mentioned earlier, he's been keeping that data up to date, and you can see that's always, it's still, there's a downward trend out through early 2014, but you can see there's kind of a curve in it, and it looks like it's starting to level off. So are we going to get to 1500 Gauss when all the sunspots disappear? Again, we'll just have to wait and see. It's an interesting plot, and it could be that, you know, the magnetic process on the sun continues during a solar minimum, but we just don't see sunspots. But the process is still going on. Oops, excuse me, kitty. Okay, I talked about rush to the poles. What we're looking at is a plot of the iron 14 emission regions. That's about 530.3 nanometers. For you optical guys, that's about 5,300 angstroms. This is kind of like a butterfly diagram, if you're familiar with those. The butterfly diagram plots where sunspots emerge versus time. This is plotting where those iron emissions are versus time. You can see that way on the left where that red dotted line is, you can see that those emissions kind of rush to the solar poles. That's the solar latitude there, north latitude, 0, 20, 40, 60, 80. And that's cycle 20, 20, 21, 22, and 23, and then 24, we don't see that rush to the poles up around the red dotted line. So what that says is cycle 24 is significantly different from previous cycles. Again, that could be an indication that we're entering a grand solar min, or perhaps even a Maunder minimum. From that data, those authors predicted that the northern hemisphere maximum would be in late 2011, and they are also predicting that in the southern hemisphere will max in early 2014. Now that kind of falls right in line with that earlier plot of sunspot asymmetry. The iron emissions predict that the northern hemisphere will have a sunspot peak in late 2011, and that's about where it happened. Again, you go back to the asymmetric sunspots, and the northern hemisphere is the one that dominated early on. Now the southern hemisphere is dominating, and looks like it's headed for the second peak will be early 2014, and that's probably what's going to happen. So that's an interesting way to look at all that stuff. So to kind of summarize and answer the question, are we headed into a Maunder minimum? It appears that most solar scientists believe we're going to experience several low solar cycles. In other words, it's just a grand solar min per the Gleissberg cycle. Right now, there's really nothing bulletproof to say we're headed into a Maunder type minimum, so we're just going to have to wait and see. But what if we do enter a Maunder minimum? What's propagation going to be like? Well, I've broken it up into two scenarios. The first is what's the F2 region going to do if there aren't any sunspots? More than likely, if we're in a Maunder minimum, the E region is going to be diminished a bit because there's going to be less radiation from 1 to 10 nanometers, the soft X-rays. The D region will probably be diminished a bit also because there's less radiation from 0.1 to 1 nanometer, which is hard X-rays. So what we can do is just go into VOACAP and predict, what's a path going to look like. And what I did is looked at a path from W9 to Europe in October, and I plotted two different solar cycles on there. The green is an average solar cycle, about 100, smooth sunspot number about 112. And you can see that, we're going to have some 10-meter openings for an average solar cycle, which everybody believes, I think, that the low bands are better at solar minimum. Looking further into the red line, which is 0 sunspots, it says, we can expect some 17-meter F2 propagation. 15 is going to be spotty, and 12-meter and 10-meter F2 is probably not going to be very likely. It's going to be noise. Now, I should point out that sporadic E will probably still be present, because in the bottom right there's just a plot of the number of openings during the ES season, which is May through September, May through August. Those are the number of openings from the eastern North America to Europe on 6 meters. And as you can see, that it looks like solar min is a little bit better for sporadic E. These come from actual cluster spots, and they're done by a VE3, and I can't remember what its call is at the moment. I should have probably put that on there to give him credit for that data. But what it says is, even if we're in a Maunder minimum, more than likely we're going to still have E sub S, sporadic E, so that means 6 meters in the summer, and 15, even 15, and obviously 12 and 10 will probably have sporadic E in the summer also. Scenario 2 is gets a little bit more involved. Got a little bit of math in that. 38. Okay, I'm doing pretty good. We have to remember that sunspots and 10.7 centimeter solar flux are proxies for the true ionizing radiation, which for the F2 region is extreme ultraviolet. So real question is, what's happening to extreme ultraviolet? We know that it looks like sunspots are disappearing. Does that mean the EUV is going down too? So let's go through an exercise with sunspots and 10 centimeter solar flux first. Then we'll go through another exercise with EUV and 10 meter and 10.7 centimeter solar flux. So here's a plot of all the data we have on smooth sunspots versus smooth 10.7 centimeter solar flux. Now it starts in August 47. That's when we began measuring 10.7 centimeter solar flux. Well, actually, we started measuring in February, and of course we needed 6 months of data to calculate the smooth numbers, and that's why they start in August 47. You can see that the blue dots are just the smooth solar flux, smooth sunspot number pairs, data pairs, and they mostly follow that red trend line, which is a second-order polynomial. But notice there's some anomalous data, and I've annotated it in kind of yellowish. So when did this happen? Oops, wrong way. There we go. Well, it happened after cycle 23 peak. So what we have here is the same data, but only up through December 2000 plotted. You can see we got rid of that anomalous data. The R-squared number went up a little bit. So what we can do is calculate what the sunspot should have been using the better correlation with the 10.7 centimeter solar flux in the previous slide. Then we can plot what was expected based on that better correlation against what actually happened. And there's the plot. Up through the peak of cycle 23, the smooth sunspot number and the smooth 10.7 centimeter solar flux agreed very well. Now there's some anomalies at solar cycle peak, but we'll kind of ignore that. But after cycle 23, it's obvious that the sunspots are lower than what they should have been. And what that is saying is it's probably what Livingston and Penn are saying, that we just can't see sunspots anymore as good as we used to. Again, this still doesn't address EUV, so what we can do is go through the same exercise with 10.7 centimeter solar flux and EUV in the 26 to 34 nanometers. That range is responsible for about half of all the ionization in the F2 region, so it's a good indication of what's going on. So I downloaded a whole bunch of data from the Solar Heliospheric Observer satellite, and unfortunately we don't have as much data because we had to wait till we get satellites up above the atmosphere to start measuring EUV, because the EUV is absorbed in the ionization process, so we can't measure it at ground level. And it showed the same anomaly when I plotted all the data. And all the data means it started in about July 96. And you can see that a lot of it on the top plot, a lot of it follows that red trend line very closely, except that anomalous stuff at the lower left of the trend line. So if I assume that something happened at the peak of cycle 23, take that data out, after cycle 23, and you can see the plot is, the correlation is really excellent. So we can go through the same thing, and what it says is it sure looks like EUV, which is the blue, has decreased after the peak of cycle 23. It's not as high as it was expected to be based on the excellent correlation before cycle 23 peak. But if you take a little careful look at the previous graph with the sunspots, it said they decreased to about 70% of the expected value, but the EUV decreased to only about 82%. So maybe that suggests that the EUV won't be decreasing as much as the sunspots. So what does all that mean? It says, well, we really need more EUV data. We just don't have enough of it. So all of this is speculation. And of course, buyer beware is very appropriate here. But maybe a Maunder minimum, if we enter one, won't be as bad as we think if the EUV doesn't decrease as much as sunspots. What that would do is probably move 15 meters from spotty to good. We'd still probably not have any 12 or 10 meter F2 openings. Again, sporadic E would probably still be present in the summertime. So summarizing this, all this stuff, sure looks like something inside the sun changed around the peak of cycle 23. There's lots of evidence that we're entering a grand solar minimum. But I don't think any of the solar scientists are 100% sure yet that we're going to see a Maunder type minimum. Now, if it is, 15 meter F2 will be spotty, and probably 12 and 10 will be noise. If it's a Dalton type minimum, we'll probably experience propagation kind of like what we're experiencing right now with this solar cycle. Now, the good news is we're going to collect some really good data, I think, in the next 10 years to hopefully explain what the sun is doing, how it impacts a grand solar minimum. Now I say 10 years because that should cover the decline of cycle 24 and the ascent of cycle 25. So hopefully we'll maybe get a better understanding of what the sun is doing. So now we come to the answer to the pop quiz. And both of those call signs, the X indicates they were experimental stations, and they were early TV stations. Now, it just so happens that April 2014 is considered the 75th anniversary of TV. In fact, it's April 30th. That's when W2XBS inaugurated regular television broadcasting at the opening of the 1939's World's Fair. They also televised the first Major League Baseball game on August 26, 39. That was the Brooklyn Dodgers versus Cincinnati Reds from Ebbets Field. You older hams like me will remember the Brooklyn Dodgers and also Ebbets Field. And W2XBS eventually became WNBC, and I think the stroke 4 means Channel 4, and I think that's in New York. W3XE, similar. They televised the 1940 Republican National Convention in June of 40, and now they're KYW TV in Philadelphia. So, Ken, that's all I had. Yeah, we got time for questions. So.
Okay, very good. I'm guessing that wasn't in high definition at the time.
Probably not.
Not even color, for that matter, huh?
Probably not.
Yeah, okay.
I bet you it was pretty grainy too.
Yeah, I would think so.
Yeah.
Okay, very good. Well, folks, here's your chance to test the expert. If you got any questions for Carl, go ahead and fire those off to us now, and we'll take those. And I'm kind of torn on this subject because as you mentioned, there's nothing like for us here in North America, nothing like a nice 10-meter opening to Southeast Asia. And we've had some good openings here the last few months, but also being a low-band aficionado and putting some work into my low-band antennas, I'm hoping that's going to pay off here too if we do actually sink into another minimum. So
let me make another comment on
sure.
On the experimental stations. When I got my novice license in '61, I can remember that the X in the suffix was experimental, but I don't know when that disappeared and when like TV stations went to just all letters. Maybe someone out there knows that. That'd be interesting to just bring up.
Sure. Okay. All right. Well, we are not getting any questions, so you've either answered everyone's questions or you've given them a lot to think about, and maybe they'll have some later on, which I guess they can send to you directly too. And your email address is, I don't think it was in the presentation, if you want to give that out.
Yeah, it's on the first page. It's k9la@awrl.net.
Okay, very good.
They're pretty interesting, pretty easy to remember.
Yep. Okay. Okay. Well, I guess that's going to do it then. We'll go ahead and wrap things up. And Carl, really appreciate you taking the time to pull all the data together and put it into a presentation and spend some time with us and sharing it. It's very interesting. We are living in some interesting periods here, and as you say, maybe 10, 20, 30 years from now, we'll know what this all means. So, anything else you want to add before we close it out?
Not really. Well, there's one thing that up until probably half a year ago, I think all the solar scientists believed that that the sun was a one-cell pattern of plasma flow in the interior, and that's what all their models are based on. And not too long ago, some other scientists took some measurements and believe it's at least a two-cell pattern. So hopefully our model of what's going on inside the sun is going to get better. Maybe that'll eventually lead to some better predictions of solar cycles. So yeah, we'll have to wait and see.
Sure. Very good. Okay, well, as we get into this too, you're certainly welcome to come back. And okay, so no other questions, but I will just mention, Carl, I'm getting a ton of thanks, great presentation, etc. So your efforts were greatly appreciated. So with that, thanks again, Carl. Really do appreciate your effort and your time to be here. And thanks to everyone who joined us for the presentation. I'm working on a couple of new ones. Nothing to report at this point, but you'll be notified via our email list or on contesting.com or some of the other venues we use to announce upcoming webinars. And of course, you can always keep an eye on the WWROF webpage. And as Carl mentioned, if you haven't been there, go ahead and check them out. Doing a lot of good work, and they certainly would welcome your support as well. So thanks everyone for being here. Carl, thanks again everyone. Have a great evening, great rest of the week, and we'll see you next time. 73s, bye-bye.